So it's my absolute pleasure to introduce Richard Hain from Duke University. It's our pleasure to have him speak for us today, and he'll be speaking about Hecke actions on loops and periods of iterated Shimura integrals.
Okay, well, it's a pleasure to give this talk. So let me just share the screen here. Whoops. I want to do that. There it is. Share. So can everybody see that?
Yes,
I can, yeah, myself. Yeah.
Yeah, okay. So let me just start with a little background that you may or may not know, and then we'll move on from there. So you probably know from Payman that an iterated integral or an iterated line integral is this expression here. It's a string of one forms on a manifold, and you take a time-ordered integral of them. So an iterated integral defines a map from the space of piecewise smooth paths on a manifold into the field. So here K could be the real numbers, the complex numbers, or it could be, they could be vector valued. So, or take values in some algebra, like a tensor algebra. And how do you compute the value? You just, oops, I didn't define what the F's are. You take the one forms and you pull them back along a path. So when you pull back, say, omega 1 along alpha, it will be f1 t dt. So you write it like that, and then you take the integral of these, the product of the f's over the time-ordered simplex. And in general, an iterated line integral is a linear combination of such functions. So we want iterated integrals to be a vector space. So we'll call an iterated integral closed, or also we could call it a homotopy functional if its value on a path depends only on the homotopy class of the path relative to its endpoint. That means you can deform the path, but you have to leave the beginning and the endpoint fixed. And so closed iterated integrals give you a map, for example, from pi1 into whatever k is. You just take a representative of the homotopy class, you evaluate the iterated integral on it, and you'll get an element of k. So they're not, in general, homomorphisms. They satisfy all sorts of properties, which you may or may not know about, but at the moment, they're not so important. And I should point out that on a complex curve, iterated integrals of holomorphic one forms are always closed. That means they only depend, their value on a path depends only on the homotopy class of the path relative to its endpoints. So a very standard example is to take the manifold to be P1 minus 0, 1, and infinity, and you take the two one forms to be omega 0, which is dz over z, and omega 1, dz over 1 minus z. And then if you integrate from 0 to z, the integral actually converges, even though the integrand, omega 0 has a singularity there. And you get a multi-valued function on P1 minus 0, 1, and infinity. And the function you get is the kth polylogarithm. And so inside the unit disk, the principal branch is the sum of z to the n over n to the k. And it's the value of the principal branch at 1 is just the value of the Riemann zeta function there. So in about 2005, Manin wrote a paper where he defines iterated Shimura integrals. So these are obtained by taking a list of modular forms of some finite index subgroup of SL2Z. I suppose it doesn't really have to be a congruent subgroup, but the natural thing to do is to take gamma to be a congruent subgroup. And we'll take the form omega j to be fj to the of tau times tau to the kj minus 1, where kj is just some integer, that positive integer that's bounded above, well, that is bounded above and strictly less than the weight of that modular form. So such one forms occur, I guess, quite a lot in number theory. And an iterated Shimura integral is a linear, so here I should say tau is the coordinate in the upper half plane. And an iterated Shimura integral is a linear combination of iterated integrals of this form. So you're integrating the one forms that are basically a modular form of gamma times some power of tau that's strictly less than the weight of the modular form. Anyway, these are closed because they're holomorphic one forms on a curve. And so they define a holomorphic function or holomorphic functions on the upper half plane. Fix a base point tau 0, and the value of the function at tau is the integral from tau 0 to tau. And this will be well defined. It'll be single valued because there's a unique homotopy class of paths from between any 2 points in the upper half plane. So this also gives us a function on a function from our congruence subgroups gamma into the complex numbers. We just evaluate this iterated integral on the path that goes from tau 0 to gamma times tau 0. And if you think about what this means, you should think of the upper half plane as being the universal cover of the corresponding modular curve. And if you had a loop in the modular curve corresponding to gamma, it would lift to a path unique up to homotopy from tau 0 to gamma of tau 0. Okay, so now what's a multiple modular value? It's the regularized value of the integral, the iterated integral up the imaginary axis of these guys here. So if this iterated Shimura integral, and the powers of I are just in there, are bookkeeping. So, right. Yeah, so these are multiple modular values, and these were defined by Francis Brown, I guess, in 2014. Yeah, I was going to say something about convergence. If all of the Fs are cusp forms, there's no issue of convergence. If any of them are Eisenstein series, you may have to worry about how to regularize the integral. It's a very standard process. It's the same as computing periods of limits of limit mixed odd structures. But another way to say it is if you think about an integral from some point to a point in the q-disk, then this integral, if you take the integral to some point in the q-disk that's not the origin, so the origin corresponds to I infinity, then you'll find that this integral is really a polynomial in log q, where the coefficients are holomorphic functions on the disk of q. And so the way you compute the regularized value is to set log q equal to 0. In other words, take the degree 0 term and then evaluate the degree 0 term at 1. It sounds hokey, but it's actually extremely natural if you explain it in terms of limits of mixed odd structures. So, for example, we could take, if we take gamma to be the congruent subgroup gamma 2, and the FJs to be Eisenstein series of weight 2, so the Eisenstein, the forms that correspond to these are just going to be dz over z, dz over 1 minus z. So in other words, these forms omega 1 and omega 0, And then what we get is, for example, the multiple zeta value, zeta AB, which is defined to be this sum here, is given by this iterated integral. And that iterated integral is a very special iterated Shimura integral. So in fact, all multi-zetas occur as multiple modular values. And that you can do that various ways, either by going to gamma 2, but you can even do it with Eisenstein series in level 1, and that's a result in the PhD thesis of Alex Sard, who was a student of Francis Brown at Oxford a number of years ago. So another example is to take twice iterated integrals of Eisenstein series. So if we take Eisenstein, whoops, did I define these guys? No. Oh, yeah. Yeah, so this blackboard bold G2K denotes the normalized Eisenstein series. And so we can look at this iterated integral, or the period of this iterated integral obtained by integrating up the imaginary axis. So this is a multiple modular value of a pair of Eisenstein series, and then you have two additional weights, this A and the B. And so I think that should be a strict inequality there. Let me just note. Yeah. So you get these numbers. So what are they? And so Brown showed that certain linear combinations of these are non-critical periods of cusp forms. And so here's an example. You can take 600 times the multiple zeta function corresponding to G4 and G10 with these two weights, and 480 times the one for G4 and G10 with those weights, and you, up to this factor of pi, you get a non-critical period of the Ramanujan tau function. And so this turns out to have all sorts of interesting consequences. It explains various things that had not been previously explained, like, whoops, like certain congruences between in the depth graded quotients of multiple zeta values, for example. And it also explains the so-called its generalization for all M and N, explain the so-called Pollock relations that occur between derivations of certain derivations of a Freely algebra on two generators, and these relations correspond to pairs of Eisenstein series. Sorry, they correspond to cusp forms, and they're explained by this relation. Okay, so probably have some questions by now, and one would be that where do iterated Shimura integrals arise in nature, and what's the significance of their periods, so of multiple modular values? So another is, and it was motivation for this work, is can Brown's computations of periods of twice iterated integrals of Eisenstein series be proved using a Hecke action on, say, iterated Shimura integrals? So, right, so somebody once said to me, I don't know if this is true or a standard idea in number theory, but the person said, and I can't remember who it is, that if you see cusp forms, for example, or modular forms appear somewhere, they should be explained by an action of the Hecke algebra. So the question then is, can Brown's computations of periods of twice iterated integrals of Eisenstein series be proved using a Hecke action on, say, iterated Shimura integrals? And another question, which I won't discuss, is what's the relationship between multiple modular values for the gamma n. So that's the principal congruent subgroup of SL2Z of level n to Goncharoff's work on higher cyclotomy. That is on, for example, the unipotent fundamental group of say C star minus the nth roots of unity, or right. And so in the n equals 1 case, so basically Francis Brown, myself, and Makoto Matsumoto sort of answered this question of somehow tried to explain this point of how modular forms influence multiple zeta values for just the standard multiple zeta values. And so the answer is somehow contained in the fact that an elliptic curve degenerates to a nodal cubic. And if you take an elliptic curve minus identity, it degenerates more or less to P1 minus 0, 1, and infinity. So you can regard P1 minus 0, 1, and infinity as a very degenerate elliptic curve with its identity removed. And likewise, for higher n, you have, you can think of C star minus the nth roots of unity as being a very degenerate elliptic curve with a cyclic n torsion subgroup removed. Anyway, like I said, I'll address the first. The second is the second and the third are actually works in progress. Okay, so let me just explain relative unipotent completion, because iterated Shimura integrals occur as periods of this particular completion of, say, SL2Z. So this is the executive summary. So if I have to explain this very quickly, what I would say is relative unipotent completion replaces a discrete group, such as SL2Z, by an affine Q group. So an affine group is just the spectrum of a Hopf algebra. And in characteristic 0, every Hopf algebra is a direct limit of finitely generated Hopf algebras. And this tells you that every affine group is an inverse limit of affine algebraic groups. So such groups are called pro-algebraic groups. So affine group and pro-algebraic group are the same thing in characteristic 0. So anyway, so what we're going to do is replace our discrete group SL2Z by an affine group, and also as a Zariski dense homomorphism from our discrete group into the Q rational points of the group. And the Q rational and the group is an extension of a, I'll say, pro-reductive group. That would be an inverse limit of reductive groups. We're going to see a natural example in a few minutes, to be specified in advance. So every affine group is an extension of a pro-reductive group by a pro-unipotent group. And what we're doing is we're specifying what the pro-reductive quotient should be. And why are we doing this is because a discrete group is not motivic, or not in any sense that I understand. So, but to somehow get a motivic structure on it, we have to replace it by a vector space. And there are all sorts of ways you might imagine for doing that, but the best way to do it would be to replace the group gamma by the ring of functions on an affine group. And this group should be some sort of completion of our discrete group gamma. And so if we make the right choices, this Hopf algebra is motivic in the sense that it has a natural mixed Hodge structure, and after tensoring with the L-adic numbers, it will have an action by a Galois group, in our case, the absolute Galois group. And the connection with iterated Shimura integrals is that the coordinate ring of the completion I'm going to describe in the next couple of slides is a Hopf algebra consisting of closed iterated integrals. And these integrals are going to be more general than just iterated Shimura integrals, but it's going to contain all iterated Shimura integrals. So basically, we're taking a discrete group, replacing it by an affine group. The coordinate ring of the affine group is going to consist of closed iterated integrals of modular forms. So let me give you a more mathematical definition to describe how this works. So, oh, by the way, I should say on this previous slide, if I took the reductive group to be trivial, then the completion is just the unipotent completion. So for example, if I do this for pi1 of p1 minus 0, 1 and infinity, the coordinate ring of the unipotent completion of that pi1 will consist of all iterated integrals of those one forms I wrote down before, omega 0 and omega 1. But anyway, in the case we're interested in, or in general, we take gamma to be a discrete group, R as a possibly pro-reductive Q group, and we're going to fix a Zariski dense representation from gamma into the Q points of this reductive group or pro-reductive group. And the next thing you observe is that if you look at the following, situation. So we're going to look at affine groups, which are extensions of our fixed reductive group by a unipotent group that come equipped with a homomorphism from gamma into the Q rational points of the group. And I'm being sloppy here because I'm just going to, in general, I'm going to just skip writing the rational points. I'm going to think of a homomorphism from gamma into G as really being a homomorphism into its rational points. So if we look at such diagrams, so we've got gamma maps into R by a fixed homomorphism, and we're going to look at all homomorphisms of gamma into a group G that's an extension of R by a unipotent group. And you can easily see they form a category, and by definition, the relative completion of gamma with respect to rho is the initial object in this category. So technically there'll be many, but they're all canonically isomorphic to each other. And this completion will typically, I'll denote it with a script G, will come equipped with a homomorphism from gamma into its rational points, and it will be an extension of R by a pro-unipotent group. So we want to do this with SL2Z. So the setup here is right. So the setup here is we'll take the modular curve is going to be, I'll think of as the quotient of the upper half plane by SL2Z. So this is just the moduli space of elliptic curves, but we will regard it as a stack. And if this sounds scary, it's not, because anytime you just work with classical modular forms, they are actually sections of a line bundle in the stack sense. So to work in the stack sense just means that you're working SL2Z equivariantly on the upper half plane. So if you choose a base point in the upper half plane, it determines an isomorphism of pi1, the orbifold or stack pi1 of y with that base point with SL2Z. And specifically, the element gamma of SL2Z maps to the loop that corresponds to the unique homotopy class of paths from your base point in the upper half plane to gamma times that base point. If you think about standard covering space theory, this is the natural thing. And so it turns out, just as in the case of P1 minus 0 and infinity, the most natural choice of a base point is actually a tangential base point at the cusp. So the coordinate disk around the cusp of the modular curve is the Q disk, and you can take the tangent vector ddq. And so if this is sort of unfamiliar, you should think of, so if you map the upper half plane to the Q disk, the imaginary axis goes to the positive real axis. And the closer you get to infinity, is the closer you get to the origin of the Q disk. So you can think about this tangent vector as being the germ at infinity of the interval from IY up to I infinity. Anyway, so it turns out there are two, from the point of view of this talk, there are two natural choices of relative completion of SL2Z. I'll call one the small, and I'll call the other the large. So the small is the subject of various papers that I've written, and also Francis Brown's paper on multiple modular values. But for the Hecke story, we have to work with the large one. So the small completion, we take the reductive quotient to just be the affine group SL2 over Q. And the homomorphism rho will just be the inclusion of SL2Z into SL2Q. And so this completion is an extension of SL2Z. And in fact, the pro-unipotent radical, it will be free in the sense that its Lie algebra is going to be a free Lie algebra, and that free Lie algebra is in fact infinitely generated. In fact, it's an Lie algebra in the category of SL2 modules, and it's basically generated by all modular forms times a corresponding representation of SL2. So it's extremely large. And so the coordinate ring of this completion, it consists of all closed iterated integrals of elements that are smooth modular forms for SL2Z with a log singularity at the cusp. So this is not quite accurate, but it's true to first order. So I have a paper somewhere with a precise description of what forms you take here. Anyway, so this coordinate ring contains all iterated Shimura integrals of level 1. And the homomorphism from SL2Z into this group takes a path to the maximal ideal of such iterated integrals that vanish on the path from the C gamma that goes from tau 0 to gamma tau 0. Okay, so evaluation on that path is the homomorphism from this ring of iterated integrals, and there'll be a maximal ideal which corresponds to those that vanish on this path C gamma.
Richard, can I interrupt? Ask a quick question here. It's about the construction of the relative unipotent completion. Does it behave well with respect to pullback? So if I look at the five, if I restrict this to the identity element of SL2, would I get the classical unipotent completion?
No, it'll be a quotient. So for example, H1 of the unipotent radical will be a representation of SL2, and there'll be the unipotent completion of SL2Z is trivial because H1 of SL2Z is trivial. This Lie algebra here, in fact, let me try to switch here if I can. Can I? I'll do it later, but basically the H1 of the abelianization of U is infinite dimensional.
I see.
And it's basically I'll tell you what it is. The H upper one is the direct sum over all n of H1 of SL2Z with coefficients in, say, S2nH, the 2nth symmetric power of the standard representation of SL2, tensored with the same representation, S2n of H. And you sum over all n. So those H1s are basically consisting of holomorphic modular forms and anti-holomorphic cusp forms. And you're tensoring all of those, each with the corresponding representation of SL2. And so it's extremely large. And so the unipotent completion would only correspond to taking n equals 0, but H1 of SL2Z with coefficients in Q is 0.
Mhm.
So you get, there's no unipotent radical. I mean, it is functorial. Yes, if you have a homomorphism from gamma into R and into R prime, there'll be a homomorphism from the corresponding relative completions.
I see. Thank you.
Anyway, every profinite, we're going to see another instance of that right here. So every profinite group can be regarded as a pro-reductive group. So the way to think of this is you just have to see that every finite group can be regarded as a reductive group, and it can. The ring of functions on the corresponding group is just the dual of its group algebra. It's just the functions from the finite group into, say, Q. And so that's a Hopf algebra, and the rational points of the corresponding group is just the original finite group. And so if you have a profinite group, it's an inverse limit of finite groups, so it's actually can be regarded as an inverse limit of algebraic groups, and each of these groups is in fact reductive because the group's finite. So what that plays a role here, because to get the large completion, we're going to take the reductive quotient to be SL2 over Q. So that's the standard SL2 over Q. And then we take the product with SL2 of Z hat. So Z hat is the profinite completion of Z. If you like, it's the product over all ZP, all the p-adic integers. But it's a pro-reductive group. It's the inverse limit of SL2 of Z mod n as you let n vary. And so it's a pro-reductive group. And the homomorphism from SL2Z into here is the diagonal one. It'll map into SL2Z hat in the obvious way, and it maps into SL2Q in the obvious way. And it's a nice little exercise, it's elementary to show that that's Zariski dense. So you get a completion, and it can be described, in fact, it's described in detail in this paper I have on the archive about the Hecke story. So it's an extension of this pro-reductive group. So this is not reductive, it's pro-reductive by some pro-unipotent group, and this pro-unipotent group is in fact free. So it's Lie algebra is free, and it's got it's H1 instead of just involving modular forms of level 1, it'll involve modular forms of all levels. And it will also contain all continuous functions from SL2Z hat into K. So for example, Q or C. So these are just the functions that factor through a finite sum SL2Z mod n. And I should say here, if you take the homomorphism from this reductive group, you can project onto SL2, and that will give you a homomorphism from the large completion to the small completion. So the large completion has lots of nice properties. I mean, it's annoying that it's so large, but it's also good because it involves modular forms of all levels, whereas the small one involves only modular forms of level 1. All right, so for each choice of a base point in the upper half plane, there are natural mixed Hodge structures on the coordinate rings of both the small completion and the large completion. I mean, that's really a special case of a general theorem. And we got, for various reasons, we're going to take the base point to be the tangential one. And we're doing that here for the same reason you do it with P1 minus 0, 1, and infinity. You want an integrally defined base point that has everywhere good reduction. And any other point on the modular curve, if it corresponds to, say, an elliptic curve over Z, will have bad reduction somewhere, right? Because you just take any prime dividing the discriminant of that curve, and if you reduce mod P there, you will get a singular elliptic curve. So that's not a good choice of a base point. But this tangent vector here is non-zero mod P for all P. All right, so then if you tensor with QL, you can prove there's a natural action of the absolute Galois group on both. So for example, the coordinate ring of the large completion looks like a motive, as it has compatible Hodge and Natal realizations. And there's also a natural Q de Rham structure. So in fact, all these iterated Shimura integrals I wrote down, if you make the right choices for the modular form, the right scaling, so for example, Hecke eigenforms, normalized Hecke eigenforms, then you basically get a Q de Rham structure from them and their non-holomorphic analogs. And so you get periods. And the periods of this guy contain all of Brown's multiple modular values. And so they are, as I pointed out before, they're iterated Shimura integrals evaluated on the imaginary axis, or if you like, just evaluated on the standard element of order 4 in SL2Z. So what does this mixed Hodge structure look like? Well, its weight-graded quotients are all of the following form. You can take, if you take a whole bunch of, say, Hecke eigenforms, they say F1 through Fm, each will have a standard, if you like, motive associated to it. So a standard Hodge structure and Galois representation. And you can take symmetric powers of those and take tensor products of those where the modular forms are different. And so these are basically supposed to be the simple motives of this type. And you tensor them with some symmetric power of H1 of the elliptic curve corresponding to a base point, and you take a take twist of that. So you get these guys here, and I should point out, if you take the tangential base point, this symmetric power of H will just be a sum of take things, because H1 of this first order smoothing of the nodal cubic is just Z of 0 plus Z of 1. Anyway, but you can ignore that. So basically you've got all these interesting motives here, tensored with some representation of SL2, and after rearranging things and taking SL2 invariants, you generate lots of extensions of Q of 0 by these motives here. And so such extensions are the subject of a conjecture of Beilinson. So the question is, do these conform to Beilinson's conjectures? And so there is a wrinkle here. In fact, before I tell you about the wrinkle, so part of Brown's motivation here was to try to generalize his theorem about P1 minus 0, 1, and infinity in the Tate case to the modular case. So his theorem in the Tate case says that if you like, the coordinate ring of the unipotent completion of pi1 minus 0, 1, and infinity with the correct base point generates the category of mixed Tate motives over Z. In other words, the mixed Tate motives with everywhere good reduction. So what he wants to do in the modular case is to say, what he's asking is whether the coordinate ring of the small relative completion of SL2Z generates all the extensions of Q of 0 by such motives here as predicted by Beilinson's conjecture. You should get no more, no less. Unfortunately, there's a wrinkle. I mean, Hodge theory tells you can't get quite all of them. You miss out on just a few. So it's an interesting question to wonder whether maybe those things don't really occur, or so or where else you might find them. So, but the goal still is to show that the coordinate ring of the small relative completion generates almost all of the extensions of Q by such motives predicted by Beilinson. And another question is, does the Hecke algebra act on, say, the group algebra of SL2Z, the coordinate ring of this large completion, or its periods? And if this is the case, can you use it to either try to find these extensions, or can you use it to explain Brown's computation of the periods of twice iterated integrals of Eisenstein series that I wrote down before? Okay, so this moves us to the third part of the talk, which is about the Hecke action. So I'm going to call a correspondence an étale correspondence if the maps G and H are étale, so just finite unramified coverings. And the correspondences that give you Hecke operators are examples of étale correspondences. And they act on, for example, homology. This correspondence I wrote down acts on homology. You would pull a homology class back under G and push it forward under H. I should say, strictly speaking here, I don't need H to be étale, but all the examples we have in, that we consider will be étale on both sides. All right, so the question is, do étale correspondences act on the group algebra of, say, pi1 of X? So X is the space at the bottom of the left, X is the black dot. So here, all the points upstairs is U. So I'm using this picture here. X is on the bottom left, Y is on the bottom right, and U is upstairs. So this would be the left-hand map would be of degree 5, say. And its various pre-images are there. And if you want to specify the Hecke action, you would want the correspondence to be a correspondence of pointed spaces. So and when you map down the other way, the fiber of the left-hand map over the base point may not map to distinct points on the other side. So here there is one fewer point, and that's because one point got doubled up, okay? Not a big deal. So we make a choice of what the base points are, and now we try to get the Hecke operator, this correspondence to act on pi1. So if we take this loop here that happens to lift to a closed loop, and that means it's already in pi1 of U with that black base point, we can push it down and everything is great. Everything works as expected, but there's a problem. Some loops we have downstairs won't lift to a closed loop upstairs. In fact, that's going to happen a lot of the time. When you project down, you don't get a loop, you get a path. And if I took other blue paths, they could end up at any of these points here. And so that's a problem. So Hecke correspondences, in no way that I can imagine, can a Hecke correspondence, an étale Hecke correspondence map from the group algebra of pi1 to the group algebra of pi1. It's going to map to something else. It's going to be some sort of sum of path torses. And if you try to pursue this, which I did for a while, you get a total mess, because when you compose these guys, you get gazillions of base points, and you don't want to do that. So the problem can be avoided by working with conjugacy classes. In other words, with unbased loops. So I'm going to denote by lambda x the free homotopy classes of maps from the circle into X. Here I'm not assuming that X is connected. And so for a group, we can define bold lambda of gamma to be the conjugacy classes in pi1, inside gamma. And so if you have a connected space, path connected space, then the free homotopy classes of maps of circles into X is the same as conjugacy classes in Pi1 standard exercise. So, okay, so now let's denote the free K module they generate by these symbols. I should say why I chose lambda. I chose lambda because Pi1 is Pi's Greek, and that's for loops. So here, sorry, I chose lambda here because lambda is the Greek letter for L, and L stands for loops. So anyway, so these invariants are covariant under maps from, say, Y to X, or homomorphisms from gamma prime to gamma. They behave well. All right, so what about pullback? So pullback was a problem with elements of Pi1. What about with just loops? So it turns out everything works well here, because if you want to pull back, so we've got an Natal covering Y to X. And how do we pull back a loop? We restrict the covering Y over X to alpha. So we pull back along alpha, and if you pull back along a covering along any map, you get a covering. And every finite covering of the circle is a disjoint union of circles. And so these circles could have various degrees over the base. It doesn't matter. And so each gives you a circle in Y, and you define the pullback to be the sum of those. And if this looks like a bunch of formulas, let me show you a picture. So here's an example. If we take, so I've put the base point in here. We don't really need the base point, but let me put it in here. So this map has degree 8, because the black point has 8 pre-images. And now we're going to restrict the covering to the red circle in the base. We find out that we've got the restricted covering has 3 components. There are 3 circles. One has degree 1 over the base. The other one has degree 3. And the third one has degree 4 over the base. And so this is the pullback map. And it's interesting to note here that if you take pi upper star and then push these guys down, pi lower star, you get alpha plus alpha cubed plus alpha to the 4th, which is not 8 times lambda. So this is an important difference with the standard, what normally happens under correspondences. If you pull something up and push it down, it typically gets multiplied by the degree of the map, but that does not happen here. If you took homology classes, the sum of the homology classes of alpha, alpha cubed, and alpha to the 4th is 8 times the homology class of alpha. But the pull up and push down is not 8 times alpha. And that's somehow hidden in what's going to happen later. So it's now easy to see that Natal correspondences induce maps from, say, Z lambda X into Z lambda Y. And they behave well under composition. If you have the product of 2 correspondences induces the product of the corresponding maps. Right? So if you take composable correspondences, they induce composable maps. All right, so now, let's look at an example of how this works. So if we had one loop down here on the bottom left, we don't need to add the base point. I just happen to put it in. This is the correspondence I drew in the cover I drew in the first place. But if you pull it up, you get 2 loops. One's closed and the other one has degree 4 over the base. And now we can push them down in the other direction. And here, 2 of the black dots get mapped to the same dot. So you get some guy that looks like this. Okay. So, so how do Hecke operators work? Well, we're going to let cov n for an integer n that's at least 1. We're going to look at the moduli space of isogenies E prime to E of elliptic curves. And this guy has two projections to our modular curve y. You can take the correspondence E prime to E and map it to its target or its source. And that is the standard Hecke correspondence Tn. And if n, and I should point out, cov n is connected if and only if n is square free. And in the case when n's prime, cov n is just the modular curve y0p. Boy, I'm running out of time here. So, right. So the Hecke operators act on the group algebra of SL, sorry, on this free abelian group generated by the conjugacy classes of SL2Z. They Tn and Tm commute when m and n are relatively prime. However, things get more interesting if you focus on a single prime. So I'm going to let EP be the map from Z lambda into Z lambda that you obtain by pulling up and pushing down along the map from cov P down into Y. So cov P is just Y0P. So you pull a loop up, push it down. And since pi in this case has degree P plus 1, when you subtract off the identity, this map essentially, this operator essentially has degree P, but it's a non-commutative kind of P. And so the first place this appears is the relation between the TP to the N. So these satisfy the following relation, that if you take TP to the N, compose it with TP, it's not TP to the N plus 1. I guess it isn't in the standard case, but it's going to be TP to the N minus 1 composed with EP. And so this may look like the standard relation. However, TP does not commute with EP. And since TP squared is TP, all squared is the same as T of P squared plus EP, you see that TP does not commute with TP squared, unlike in the classical case. All right, so I'm going to skip this slide. I'll say a little bit. The EPs are not satisfy algebraic relations. They're written down here. At the moment, it's not playing a huge role in the theory, but it's interesting to write down this non-commutative Hecke algebra. So I'll set TP hat to be the free associative algebra generated by symbols CP and EP. I mod out by this relation I didn't explain. And then I'm going to take T hat to be the restricted tensor product of these algebras. And this guy is going to act on the, oops, I wrote something down too soon there. All right, I'll get back to that. This guy acts on the, let me just get there. Okay. So it's going to act on the group algebra of SL2Z. All right, so here's the dual version. We're going to take, I'll put CL of our G hat is going to be the elements of the coordinate ring of G hat that are class functions. They're constant on conjugacy classes. So these are going to be iterated integrals whose value on an element of SL2Z depends only on its conjugacy class. And so the elements of, I'll call them length 0, these are, as an algebra, these are generated by trace. So you could take a trace of an element of SL2Z, or on the characters of SL2Z mod n, evaluated on an element of SL, the image of an element of SL2Z. So there's nothing surprising there. Length 1 is very interesting. So if you take a modular form of weight 2n in level 1, you can do this for higher level, it's just more complicated. And so there's a corresponding 1 form on the upper half plane that has values in the S2n minus 2th power of the standard representation of SL2, and I'll denote it by omega f. And the coordinate ring of SL2Z is in fact just the direct sum of the duals of the endomorphism rings of each of the irreducible representations of SL2. So that's just the endomorphisms of a whole bunch of copies of the endomorphisms of symmetric powers of H. So this means that, standard representation theory, this tells you that the coordinate ring of SL2 contains a countable number of copies of S2NH, because it'll occur in endomorphisms of Sn of H, Sn plus 1 of H, N plus 2 of H, and so on. So choose any copy of S2N. Yeah, I should have S2N minus 2 here, another typo. All right, and now we can compose our one form with that homomorphism, and we get a one form with values in the coordinate ring of SL2. And so now we can get a conjugation invariant, if you like, iterated integral of length 1 on SL2.
Sorry, Richard, where is the S2n minus 2?
Yeah, so if you have a modular form of weight 2n, then the corresponding representation of SL2 is 2 smaller. It's S2n minus 2.
Right.
I could have, maybe it would have been better if I said I took a modular form of weight 2n plus 2, and then I could have had all the representations would be S2n's. I'll fix this up and post the notes. But anyway, so what happens here is you get a conjugation invariant function in the following way. You integrate this one form over alpha. So you fix an alpha, and it will have a starting point and an end point. So you integrate this guy, and you get an element of the coordinate ring of SL2. And then you evaluate that on alpha. So you're using alpha twice. You're integrating over alpha to get an element of the coordinate ring of SL2, and then you're evaluating that on alpha. It's a nice little exercise to prove that that's conjugation invariant. All right, so the ring of class functions here, I should say it's huge. It's infinitely generated over the stuff as an algebra over the stuff of length 0. The ring of class functions on G hat has a natural mixed Todd structure and a natural action of the absolute Galois group. I guess I'm running out of time here. After tensoring with QL, neither depends on the choice of a base point. And the weight graded quotients now are all just these things that are the subject of Bailenson's conjectures. These should be the pure modular motives. Right. So I'll just state this theorem and then stop. I mean, I've got more stuff, but so the theorem says that each Hecke correspondence induces a dual Hecke operator on the class functions on the big completion of SL2Z. If I took the small completion, the Hecke operators don't act. They somehow, you have to go up in level partly here. Seems to be no way around that. Anyway, this is a morphism of, each is a morphism of mixed Todd structures, and each is Galois equivariant after tensoring with QL. And the action is dual to the action of this T hat on the group algebra of SL2, sorry, the action on the free module generated on the conjugacy classes of SL2Z. In addition, the Adams operations, so these are defined by Cm of f is just evaluated on alpha is just f evaluated on the mth power of alpha. So this is a standard thing you do with, say, characters of a group. These are also morphisms of mixed Todd structure, and they also commute with the Galois action. Yeah, let me just see if there's anything else on. Yeah, so maybe I'll stop there and let you guys ask questions.